This is the final content in Module 2 on energy demand. After watching this lecture, you should be able to complete problem set 1. Let's talk about short versus long-run energy demand. Last time, we had consumers taking the price of a unit of energy service P as given, and they choose their utility maximizing quantity of energy service Q. P is the product of the energy price, PE, subscript E, and the energy intensity, little e. So P is equal to PE times E. So for example, the price of gasoline is P subscript E is $3 per gallon, and my Chevy Aveo uses lowercase e 0.033 gallons of gasoline per mile, then we can take the product of those two, and therefore the price of the energy service is lowercase p, which is roughly equal to 10 cents per mile. In the short run, if the price of gasoline increases, consumers choose a lower quantity of gasoline. Obviously, that's the law of demand. But in the long run, consumers are also going to switch to a more fuel-efficient vehicle. Right? So if PE increases, consumers also choose to purchase goods with a lower E, lowercase e. How do households choose their durable goods? We can model how households choose their optimal bundle of durable goods as two separate steps. For each possible bundle, let's calculate the optimal utilization and therefore the maximum value of utility for that bundle. So we're going to look at bundles of goods within a household, refrigerators, vehicles, air conditioning, etc., and figure out the bundle of the goods that maximizes utility. And then we pick the bundle that gives the highest utility by discounting the utility from future utilization and account for differences in initial costs. So the next few slides are going to be on aggregating up the future utility use of a good. Optimal choice of durable goods. To make this problem simpler, assume that the rebound effect is small enough that we can ignore differences in future consumption utility. Energy prices are also constant. That's an assumption we're going to make. We'll compare different appliance options solely by the difference in future operating costs. So let's look at an example. Which refrigerator should you buy if you go to the store and look at two different refrigerators? In this example, Matthew is buying a refrigerator and comparing two models, a Samsung and an LG. The Samsung costs $1,000 and uses slightly less electricity, kilowatt hours per year, than the LG does, but the LG costs only $900 to purchase. So which one's better? Refrigerators are otherwise identical. Matthew plans to own the refrigerator for 15 years. We need to know how long Matthew's going to use this in order to discount the future utility that Matthew is going to receive from this refrigerator. So after 15 years, we're going to assume he gets $0 for the refrigerator. In other words, you can't sell it for anything. So the scrap value is 0. Assume that Matthew's price of electricity is 12 cents per kilowatt hour and he has an annual discount rate of 10%. Which refrigerator should Matthew buy? Well, we need to account for how money is worth more now than it is later. One simple way to approach this problem would be to calculate the total cost of buying and owning each refrigerator. So the total cost for the Samsung is $1,000, the purchase price, plus 15 years times 325 kilowatt hours per year to multiplied by 12 cents per kilowatt hour. So that's $1,585. The total cost for the LG is equal to $900, the purchase price, plus 15 years times 400 kilowatt hours times 12 cents per kilowatt hour equals $1,620. These calculations, of course, show that the total cost for the Samsung is lower, but they don't account for how money today is worth more to Matthew than money in the future. They're simply multiplying the energy use times the price, assuming the price is constant, over the 15-year lifespan of the refrigerator. So let's review the time value of money. Which would you rather have, $100 now or $100 in 10 years? Hopefully your answer is $100 now, because if you took the $100 now, you could put it in the bank, and in 10 years you'll have $100 plus the interest you earn along the way. In the bank, the $100 will become 1 plus R times 100 after 1 year. After 2 years, it'll be 1 plus r times 1 plus r times 100. So in other words, 1 plus r squared times 100 after 2 years. After 3 years, that's going to turn to 1 plus r cubed times 100 after 3 years. After 10 years, that would be 1 plus r to the 10th power times 100. And r is the interest or discount rate. So this is telling us how much interest will accrue if we put $100 in the bank now at an interest rate of r. Now suppose you're going to receive $100 in 10 years. What is the present value of this future payment? In other words, how much would you have to put in the bank now to yield $100 in 10 years? Instead of multiplying by 1 plus r to the 10, we'll need to divide by it. This is called the discount factor. Suppose that the annual interest rate is 5%. What is the present value of $100 in 10 years? Well, the equation at the bottom of the screen tells us this. So the present value, PV, is equal to 100 times 1 over 1 plus the discount rate, which in this case is 5% or 0.05, to the 10th power. And this is equal to $61.39. So what this is saying is that if at an interest rate of 5%, if we invested $61.39 right now, in 10 years we would have $100 in the bank. So summing this up, money today is worth more to Matthew than money in the future. Hence, future savings need to be discounted back to the equivalent in dollars today. The Samsung offers a higher price today in exchange for reductions in 15 years of electricity bills. If Matthew's annual discount rate increases, will he be more or less likely to prefer the Samsung? In other words, if his discount rate increases, he's going to value money today more than he values money in the future. If his discount rate is 0, he's indifferent between money today and money in the future. So the question you need to ask yourself is, if Matthew's annual discount rate is increasing, if it goes up to 100%, for example, will he be more or less likely to prefer the Samsung? He prefers money today over money in the future. The Samsung offers a higher price today in exchange for reductions in 15 years of electricity bills. The LG has a lower price today, so he's paying more for the Samsung today than he would the LG. Which one is he going to prefer with a higher discount rate? There's a simple formula we can use to solve this type of problem. Let's consider a stream of future payments of size x over the next t, capital T years. Assume the first payment is received 1 year from today. That's simply a way to deal with the t, counting up in the stream of future payments. If the discount rate is lowercase r, the present value of these future payments is given by the following formula. Present value equals x times AF. So the stream of future payments of size x times AF, where AF is equal to the formula on the screen, and it's called the annuity factor. I'm not going to go into how we derive the annuity factor. You will need to know this for your test, but you won't need to know how to derive it. This formula comes from a geometric sequence, and again, we will not derive it. So what is Matthew's annuity factor in this problem? Using the formula, we can calculate it. So the annuity factor is the formula there, with R as the discount rate. For Matthew's refrigerator decision, T equals 15 years, capital T that is, and R equals 10% or 0.1. And plugging these values into the formula, we see that the annuity factor is 7.61. Recalculating the total cost, this time discounting future electricity costs. So when we first looked at the total cost of the refrigerators, we were not discounting. Now we are going to be discounting using this annuity factor. And we found the annuity factor was 7.61. We also know that the present value equals x times the annuity factor. What is x in this problem? So the total cost for the Samsung is $1,000 for the upfront cost of purchasing the refrigerator, plus the annuity factor times the kilowatt hours, 325, times the price per kilowatt hour, 12 cents, which is equal to $1,297. So the total cost for the Samsung, considering discounting, is $1,297. The total cost for the LG, on the other hand, is equal to the upfront cost, $900, plus the annuity factor, times 400, which is the kilowatt hours of electricity used for this refrigerator, times the price of electricity, 12 cents per kilowatt hour, which is equal to $1,265. Therefore, considering discounting, Matthew should buy the LG. It's important to note that the 15 years is incorporated in the formula for the annuity factor, so we do not need to multiply the operating cost by 15 anymore. So in the original calculation, we had 15 times 325, or 15 times 400, but now the 15 was calculated in the annuity factor on the previous slide, which gave us 7.61. So in other words, we are valuing the future electricity payments less than we had been before because of discounting. Now, of course, Matthew should buy the LG. It's not clear, though, that this is a good approximation of consumers' decision making. When you go to the store to think about which refrigerator to buy, are you doing this calculation in your head? Not necessarily. In reality, people are often observed to make what appear to be incorrect decisions about their choice of durable goods. Especially, they choose products with a lower initial cost today, even when this will be outweighed by higher energy costs in the future. So we might see this in the purchase of a vehicle. We might see somebody choosing between a non-hybrid version of a car and a hybrid version of a car. It's exactly the same car, but one is a hybrid. The hybrid is clearly going to have lower miles per gallon than the non-hybrid, but the hybrid costs slightly more initially, and so people end up choosing the non-hybrid version, even though they could save money on gas by choosing the hybrid version over the lifetime of the vehicle. This phenomenon is known as the energy efficiency gap. The definition here is the energy efficiency gap is the non-adoption of energy-conserving technologies by consumers in spite of the apparent cost-effectiveness of these technologies. Again, the hybrid, non-hybrid vehicle. So is there really an energy efficiency gap? Well, a lot of people think that there is. McKinsey & Company, in a 2009 report, among others, finds there is a large gap, and this evidence often relies on engineering estimates. There is one paper in the economics literature that is, however, skeptical, at least in terms of household weatherization. They find that the upfront cost of weatherization in a household, like installing new windows, is about twice the actual energy saving cost. So it's not quite as energy efficient or economically efficient to invest in, for example, better windows than we had originally thought. Slightly different than the energy efficiency gap, we have behavioral energy conservation programs. And this is the TED Talk that I've asked you to watch on the previous part of this module. Economists have often focused on how prices affect demand. So we typically think about how consumers respond to price. This is the law of demand. But we also know that consumers respond to other things besides price. And this is what behavioral economics is about. It's about how consumers respond to things besides price. There's a growing interest in behavioral interventions such as information provision. In other words, for home energy consumption, maybe we provide consumers with information on ways to conserve energy. This is not a change in the price of electricity or energy, but a change in how consumers perceive their energy consumption. We might provide commitment contracts, things that cause consumers to commit to certain behaviors. And then appeals to the public good. We might send consumers information on what their energy use is doing to the environment. And we might send consumers information on social comparisons. And we'll see an example of this on the next slide. O-Power is a well-known example of a behavioral intervention, and it's a social comparison intervention. If you live in Fort Collins, you'll see something like this if you get your energy bill at your house. Fort Collins Utility sends these little notices in the mail that compares your energy use and your water use to similar neighbors, and that's what we're talking about here. Opower was just the first to do this in the country. Opower designed their program so that its effects could be easily measured. It's a randomized controlled trial for each utility. In other words, they send these letters to a random sample of households in their community and see how those letters, those social comparisons, affects people's electricity and water consumption. Hunt Alcott was the first to analyze one of these experiments. He analyzed the Opower experiment in 2011 and found that the program led to a 2% decrease in energy consumption. And we can compare this to the price change needed to get a 2% decrease in energy consumption and see how social comparisons work, see how well they work. This is what the Opower treatment looked like, similar to the ones you might get in Fort Collins, except in the Opower treatment, consumers also got a little smiley face if they were doing a good job. They got 2 smiley faces if they were doing a great job relative to their neighbors or consuming less than their neighbors, and they got no smiley face or frowny face if they were consuming more than their average neighbors. This concludes the energy demand portion of this module, and next up you should be doing the problem set.